Hello everyone, my name is Andrei Graur from Stanford University, and today I'm going to be talking about efficient splitting of necklaces. This is joint work with Professor Noga Alon from Princeton University, who is also affiliated with Tel Aviv University in Israel. So first, we're going to be starting with a definition. So the necklace splitting problem is a problem concerning the fair partition of a necklace with beads of n colors among k agents. And so a more formal definition is that for each instance, for n colors and k agents, we have a set of ordered bits. We can imagine them, let's say, on a line, each colored with exactly one of the colors I from 1 up to n. And our goal is to split the necklace into intervals and distribute them to the k agents so that some properties are satisfied. The first property, I guess we can refer to as equity. So for each color I, every agent must get either mi floor of mi over k or ceiling of mi over k, beads of that color, where mi is the number of beads of color I. And so what do we mean by that? Well, basically, we want all of them to have almost, all of the agents to have almost the same number of beads of a specific color. So we want to have that for each color I. And we would call such a solution or such a partition of the necklace a proper solution, where basically the discrepancy on each color would be at most 1. And what do you mean by the discrepancy on a color? The discrepancy will be defined as the difference between the maximum difference between for two different agents between the share of beads of that color of one agent and the share of beads for the other agent. So if an agent has 3 colors, 3 beads of one color, and the other one has another agent has 1 bead, then discrepancy would be at least 2 in that case. There's multiple agents. And we want to distribute those beads on a necklace, so we want to make that partition without having to make too many cuts. We want to make at most n times k minus 1 cuts, and we want all of those cuts to be between consecutive beads. So we don't want to cut a bead in half or anything like that. So yeah. And an obvious question would be, why exactly do we care about the number of cuts being at most n times k minus 1? And so the answer to that is, I guess, twofold. First of all, for each n and k, so n where n is the number of colors, k is the number of cuts, sorry, k is the number of agents, there exist instances where n times k minus 1 cuts are actually needed to get a proper solution. So for example, how can we build those instances? Well, if the number of agents k is not too large, then we would need to give each agent at least 1 bid. And so if we construct of each color, and so if we construct a necklace that for every single color, the beads of that specific color form a contiguous region, as we have in the drawing here in the picture here. And so for such instances, we have to, since we have to give each agent at least 1 bit of each color, we would have to make at least k minus 1 cuts on each one of those contiguous regions, because we want to have at least k intervals, k non-trivial intervals to be distributed to the k agents. Each agent needs to receive at least 1 interval of those. And so n times k minus 1 cuts are needed in some instances. But also we have that n times k minus 1 cuts also suffice in every instance. This was proved in a series of papers. First in 1985, it was proved for necklace splitting for n equals to colors. Then in 1986 for k equals to agents. And then Noga Alon in 1987 proved the problem for all values of k and n. And so given those given those results, a question would be, can we find an efficient algorithm that provides such a proper solution? And as we're about to see, the answer will be no. So we're going to be discussing some hardness results. First of all, PPA and PPAD are 2 complexity classes introduced in a seminal paper of Christos Papadimitriou, 1994. And recently, Aris Filos Ratsikas and Paul Goldberg in 2018 showed that necklace halving which is necklace splitting for k equals 2 agents. So for this fixed value of k equals 2, is PPAD hard. Now, the problem of whether PPA or PPAD is in P is a major open important problem. And given this hardness result, we resort to finding efficient approximation algorithms for necklace splitting. So what do we mean by that exactly? Well, the approximation that we're going to be we care about is the one where we relax the constraint that we need to make at most n times k minus 1 cuts, but we still want a proper solution. So we're going to be making more than n times k minus 1 cuts to get a proper solution, but we don't want to make too many cuts. So we want to have some algorithms that have that don't make too many cuts. And so we actually care about two models in our paper. We're going to be discussing about the offline and online model. The offline computational model just consists of a sequence of indices, Ci, with values from 1 up to n, specify the color of each bit. So it's a simple model. And the online model, as the name suggests, we're not going to know what the necklace is from the beginning, but we are going to know k, the number of agents, and the number of colors. And for each color I, we're gonna know mi, which is the number of bits that we're about to see of that color. So at the beginning, when we haven't seen anything, we're gonna know for each color how many bits we expect to see up until the end of the necklace. And how does the model, the online model actually work? Well, at time t, we learn the value of c t plus 1, the color of bit t plus 1. And so knowing this, the color of the next bit, right? We need to decide irreversibly whether to cut between bits t and t plus 1, as it can be shown in the figure here. And if so, if we decide to cut, there's going to be a newly formed interval, and we're going to have to decide also on the spot who to assign it to, which agent to assign it to. So we can imagine that at time t, we are, let's say, sitting at bit t. We learn what bit t plus 1 will be, and then we decide, oh, do we cut like right in between those two bits, and if so, who do we distribute the interval to? Okay, so we're going to be discussing next about some previous work on approximation. The epsilon approximate necklace splitting can be defined in the following way. So it's a similar problem to necklace splitting, but here the goal would be to split a necklace so that each agent receives a fraction of at least 1 minus epsilon over k and at most 1 plus epsilon over k of the bits of each color. And so comparing this to the normal necklace splitting problem, in that problem, we wanted each agent to get basically 1 over k of a 1 over k fraction of the bits of each color. I guess plus minus 1, because maybe the number of colors, the number of bits of one color is not divisible by k exactly. So we want to get as close to that, to complete equity as possible. But here we allow some epsilon over k gap. So in this setting, the discrepancy could go on one color all the way up to 2 epsilon over k times mi, where mi is the number of bits of that color. And to discuss about previous work, Bott and Layton in 1984 gave an algorithm for offline necklace halving, which again, necklace halving, to remind the audience, is necklace splitting for k equals 2 agents. It's a special case for which we have the hardness result proved. So they gave an algorithm for this problem that provides a proper solution, making of 1 over epsilon to the n cuts. And then in 1996, Brahms and Taylor describe another algorithm for the epsilon approximate version that again makes an exponential in 1 over epsilon. So I guess it's 1 over epsilon to the O of n number of cuts, just like Bott and Layton in 1984. And next we're going to be discussing about our results for the problem. We're going to be talking about both the offline model and the online model. In the online model, we also provide some lower bounds, but we first start with the algorithmic results, so the upper bounds, and we first talk about necklace halving, which again is a necklace splitting for k equals 2 agents. First of all, we have that the first theorem says that there exists an efficient algorithm that makes at most n times 3 plus log 2 of m cuts and provides the proper solution to offline necklace halving, where m is the maximum of mi. And an important remark to make is that if we aim to get an epsilon approximate solution, um, instead of a proper solution, the algorithm from theorem 1 can be tweaked to make n times 3 plus log 2 of 1 over epsilon cuts, which is a considerable improvement from the O of 1 over epsilon to the n number of cuts made by the Bath and Layton algorithm. And for the online necklace halving, we have an efficient algorithm that makes at most O of n to the 2/3 n times log n to the 1/3 cuts and provides a proper solution. And as we can see, both of those theorems have both of those algorithms make a number of cuts that is dependent on m. In the first theorem, it depends logarithmically. In the second one has a worse dependency. It's m to 2/3. And as we show in the next slide, although it might seem like the second theorem, the algorithm makes a large number of cuts. This is actually close to optimal, close to tight. So as we have said, we have some lower bounds for the online necklace halving problem, and so for n equals 2 colors, we have an omega of square root m lower bound, so there is a gap of m to the 1/6. However, for n equals to a constant that is at least 3, so for example n equals 3, we have that the lower bound is omega of m to 2/3, and the upper bound is the same thing. So our algorithm is tied up to constants. And this lower bound of m to 2/3 can easily be extended to be omega of m to 2/3 times n for n colors for the general case, which leaves the gap between the algorithm that we provide and the lower bound to be log n to the 1/3. Also, we should mention here that whenever we have a lower bound, we provide instances where all mi values are equal, they're equal to m. So for each color, we'll be seeing the same number of bits for the online necklace. Next, we talk about some extensions. So by adapting the algorithms that we have for necklace halving, so for k equals 2 agents accordingly, we actually obtain general results for the case of k agents. And those are stated in the two theorems below. In theorem 5, for the offline necklace splitting, we make at most n times k minus 1 times 4 plus log 2 of 3km. So here we have a logarithmic dependence on m, but now we also have a logarithmic dependence on k, the number of agents. And the theorem 6 says that for the online necklace splitting, we make m to 2/3, k to the 1/3, n times log n k to the 1/3 cuts on the necklace. So here again, we gain a factor of k to the 1/3, where k is the number of agents for the general case of k agents. Next, I'm going to be talking about some proofs. I'm going to be talking about offline necklace, and then at the end, briefly about the lower bound for the online model. The upper bounds of the algorithm for the online model. In the interest of time, I'm not going to be presenting about it, but the proof relies on techniques from online discrepancy minimization. So the proof outline of theorem 1 is the following. There's three main ideas. The first one is that we're going to be converting this discrete necklace with beads into a continuous instance. And we do so by defining n probability measures, pi, each of which corresponds to the color I. So those would be probability measures on 0, 1, non-atomic probability measures. And so what exactly do we do with the beads? So we replace each bead of color I by a small interval, let's say t prime, of its colors, so that the pi measure of that interval is 1 over mi, which corresponds to 1 bead, since we're trying to basically normalize everything. That's why it's 1 over mi. That's why it depends on the number of beads of color I. And we have that for j not equal to I, pj of the probability measure of j of td prime will be equal to 0. So we're going to have something like in the drawing here, where let's say we have a bunch of small intervals, each of which we color with one color, which corresponds to kind of like defining some non-zero measure I for each I that corresponds to the respective color. Then the second thing would be that we want to make cuts so that the discrepancy will be no more than 1/2. So we want to make cuts on that on this on this continuous instance, so that um, if we look back at the discrete instance, like where the cuts correspond, the discrepancy there will be no more than 1/2. And here we will be allowed the cuts to be fractional as well, which means that we can make the cuts even in the interior of one of those small intervals created. And if the cut is actually made on one of the intervals ends, we call it fixed, because this would correspond to a cut the way that we want to cut on the necklace. So a cut between two consecutive beads, not a cut that splits the bead into two parts. And then after we obtain this kind of like fractional solution that can make that can cut the beads not necessarily how we want, but also in the two parts. At the end, we'll be shifting the cuts until all of them, or almost all of them, become fixed. And so, to show briefly how to do that, let's assume that we've reduced our discrepancy to what we want. So we have at most 1/2 discrepancy. And let's assume that we have a bunch of fractional cuts. And what we do at the end is that for each color I, we want to eliminate the number of fractional cuts that are made on intervals of color I. So in this case, color red. So we want to reduce that number to 0. So what exactly do we do at the end is that for each, while there's at least 2 fractional cuts on some color, let's say the red color, we look at who owns the intervals right before and right after those cuts. And then depending on that, we start shifting the cuts with the same speed, either in the same direction or in opposite directions, as those two cases show, those two pictures show, so that the discrepancy on that color and on all other colors between the two agents remains the same. But by shifting them, at one point, one of them will become fixed. So it turns out that one of those fractional cuts we actually become fixed, so we can eliminate a cut like that every time there's at least 2 cuts, 2 fractional cuts. And after, when we get to the point when we have only one fractional cut standing on the red color, well, we can basically shift it either to the left or to the right, and this won't increase the discrepancy of that color by more than 1. Which means that at the end, on each color, the discrepancy will be at most 3/2. But since at the end all the all the cuts are fixed, now they're not fractional, this discrepancy will have to be an integer, so it will be at most 1, which is exactly what we want. So that's how we finish off the proof once we get this nice fractional solution that has 1/2 discrepancy. And how to bring discrepancy to 1/2 in the first place? Well, for each interval I, we'll be denote the p-value of I. P of I equals to p1 of I all the way up to pn of I. And we will be doing multiple stages of a procedure. The first stage is that we split the interval 0, 1 into 2 n intervals, JR, with equal p-value, 1/2, let's say. And let's say in this case, we have n equals 3. And so we have 6 intervals at first. And for each interval, we're going to be denoting each interval JR, we denote V of JR, the n-dimensional vector that has on coordinate I, the pi value, pi of JR, or pi of J. And so we view each interval created as an n-dimensional vector, where again n is the number of colors. And we plan to assign each interval, or equivalently each vector, a coefficient CR in 0, 1, so that CR measures how much of that interval agent 1 owns. And so, for example, if CR is equal to 1, agent 1 fully owns that interval. If it's 0, agent 2 fully owns that interval. But for now, we allow even fractional ownership, let's say. And if those coefficients become either equal to 0 or 1 at some point, we call them fixed. If not, we call them floating. And when they're fixed, we don't change the coefficients anymore. And so the objective of that we set to accomplish is that we want some of the coefficient CR to go to either 0 or 1. But we want to do that while we maintain that the invariant that the L infinity norm of sum of CR VJR minus the vector that has 1/2 on each coordinate stays either at 0 or very close to 0. And why exactly do we want that? Well, basically this sum of CR VJR represents how much of each color agent 1 owns. And because we want the discrepancy to be very small, we want agent 1 to own almost 1/2 of each color, or like something very, very close to 1/2 of each color. So that's why we want the N infinity norm to be that close, that close to 0. And so at the beginning, we're going to start with all coefficients equal to 1/2. So both agents own the same amount of each interval. And so the condition that h, which is the vector of all 1/2, or with coordinates 1/2 in every components 1/2 everywhere, is equal to CR/VJR. So it's like in the figure below. We have 1/2 corresponding to each interval. And then what do we do next from here? We can efficiently find a linear dependence relation between the VJRs and subtract it from H, from our expression, so that one coefficient becomes fixed, at least one. So what does that mean and why is that true? Well, basically, since we have two n intervals and we have all of those intervals correspond to n-dimensional vectors, we can always find a linear dependence multiple times and like subtract it in the way that we want, so that one of the coefficients CR becomes 0/1. And we do so repeatedly up until only n coefficients are floating. And so what would happen? So for example, that instance from the previous slide would transform into something like this, where let's say the first three intervals are now fixed. We don't do anything to them anymore. We know how to distribute them to. And the next three intervals have floating coefficients. And then what do we do on this next stage? Well, basically, we'll repeat the process. So what we mean by that is that we cut each one of those remaining intervals in half by p-value. So we cut so that the p-value is not 1/2 right now, but will be 1/4 for each one of those smaller intervals. And so, and each one of those smaller created intervals will inherit its coefficient from its parent. So the parent being the interval that was split into two equal parts by p-value. And so again, we will have at most 2n intervals. Which is here is at most 6. We again find linear dependencies all the way up until there's at most n intervals left. And then when that happens, we again we have three smaller intervals that remain, and then we repeat the process multiple times. And it turns out that from the way that we define the algorithm, from the fact that we always cut in half by p-value, if we repeat this process log 2 of 1/epsilon times, we can get an epsilon approximate solution. And each time that we do this, we don't do more than n cuts. So the number of cuts would be in the end what we need, since we have like log 2 of 1/epsilon stages. And it's clear that from this algorithm, if we set epsilon equals to 1/2m, where m is the maximum of mi, then the discrepancy here will be at most, I guess, at most epsilon, which translated to the discrete necklace, this would yield a discrepancy of at most 1/2, which is what we need in the end for us to be able to shift the coefficient so that we get a proper solution. So this ends our proof. Okay, and now in the interest of time, I'm going to be discussing very briefly about the Alon necklace lower bound. So for n equals 3 colors, the lower bound is omega of m to 2/3, and this proof relies on the following lemma, which is that if I time t, the discrepancy on color 1, let's say, is x, and no bits of color 3 have been shown yet, and there exists some adversarial input, some way to continue the adversarial input that we've been showing so far, that forces at least x/4 additional cuts for a proper solution. And how exactly we can use this? Well, basically in the proof of the theorem of the lower bound, we use that we reserve one color, say color 3, for punishment in case discrepancy goes over m to 2/3. And if it does, then we can, obviously using the last lemma, we can force omega of m to 2/3 cuts in the end. And so we may assume that that the discrepancies of colors 1 and 2 will always stay between minus m to 2/3 and m to 2/3. So we can look at the status as a 2D vector at each time, and this vector vt is equal to xtyt, which is the discrepancies of the first two colors. We can look at that and have a function m of xi that measures kind of like the progress that we make our adversarial input makes in making the algorithm make a lot of cuts. And the idea is to always provide like the continuation of the adversarial input, the continuation of the necklace, so that this function increases by a value that's quadratic in the number of bits that we've shown. And so in the end, the proof reduces to showing using Cauchy-Schwarz to show that some quantity, the number r of cuts that is made is at least m to 2/3, because otherwise we can make a lot of progress in m, in the m value, and this cannot be possible because v final is in that m as a 2/3 sized box, and so m of v final will be bounded by something like 12 m to 2/3. So this entire discussion is made in point 7. And lastly, we're going to be talking about some open problems. The first one is that for n equals 2 colors, the gap between the upper bound and the lower bound is m to 2/3 in the online version. And so we would like to know whether we can improve the lower bound for that, or whether we can improve the algorithm for n equals 2 colors. And for the second thing would be for online necklace halving for general number of colors n bigger than 3. We have that the gap is still theta of log n to the 1/3. So it'd be interesting to see if we can get a better lower bound, maybe by defining a different potential function, or get a better algorithm. And lastly, it would be really interesting to see if the offline approximation algorithm for necklace halving can be improved to make fewer than the number of cuts that our algorithm makes. So something like O of n would be very interesting to have. That was all. Thank you for listening.